In the previous video, we discussed the foundations of physics, and we put the question marks around if the space is empty or not, which implies that there is some problem with relativity theory. In this video, we will have a look into relativity theory. We will look at the specific scenario, which should explain what is the problem with relativity theory, and it will create a starting point for new physics. So to do this kind of analysis, we will use the Bragg reflection. As we show in this image, what is a Bragg reflection? This when you take a crystal, which is a lump of material with where the distance between atoms are well defined. That is always the same distance from one atom to another. And we will have a look at a nice looking crystal. The Bragg reflection happens when the length of the let's say this phase of the wave, if you look to a photon, the phase of the photon oscillation should be the same if you are reflected from different planes within the crystal. As you see here, you have then some equation which says that you have the number of wavelengths of the photon should be equal to the distance between the layers multiplied by the angle of incidence. So since atoms are usually in the wavelengths of something like 10 to minus 11, between minus 11 and minus 10, all atoms is about the same size. So you get a certain wavelength from the photon. And when you hit the correct wavelengths, so that the phase is the same independent of the reflection, then you get an enhancement of the reflection, which gives points. So you can examine this enhancement, and you can decide the distance between the atoms. Now, for our interest in this thing, we will modify slightly this experiment, and we will use electrons instead of photons. The electrons, then this is change the name slightly. It's called the low energy electron diffraction, and this is the same thing essentially. I mean, now you reduce the speed from c down to around 10 to the 7 meter per second. And then the associated wavelengths of the electron coming from the law of Louis de Broglie, as you see from this equation. Then when you have the same wavelengths as earlier the photons, then again you have a reflection in the same way as for the photons, and you have a similar pattern coming back from reflection, as you can see here. So 10 to the 7 is quite a low velocity relative to the speed of light, which means that the effect of relativity is neglectable. I mean, you can forget about it. It's not important in this experiment, as you will see later on. So this, I should say maybe that is in the range of X-ray, of course, because when the wavelength is in the same order of size as the distance between atoms, then you have the penetration depth through a hand, for instance, and you can see it's going through in the skinny part, and the bone is absorbing the photon, and then you get an image behind. So this is X-ray range. Okay, so now you have the scenario. We have an electron beam pinging into a crystal, and you look at the reflected beam coming back, and you have nice points like this. Now we will look into relativity theory, special relativity theory. According to Einstein's postulate of for special relativity, you have essentially two rules. First, you have that all laws of physics should be the same within any inertial reference frame. and secondary, that the speed of light should be the same in all inertial reference frames. We will show that both these postulates are wrong. Because it's very simple. You take the inertial reference frame, which is essentially the observer should be the detector of something, and you just should have a constant speed. So in the laboratory, it's considered to be an inertial reference frame. The Earth is going through space with a constant speed. So this is okay. It's not quite correct, but it's okay. So now we take the electron as an inertial reference frame. The electron has a constant speed within the laboratory. So this is an inertial reference frame in the same way as a laboratory. Now there is a problem, because if you sit on top of the electron, or maybe you follow it, and you look at the associated wave of the electron, then you get a problem. How is it possible? I mean, if you sit on an electron, then the speed of the electron is 0. So the wavelengths, associated wavelengths of the electron should be infinite. How is this possible then, that you have some reflection which should be associated with the distance between the layers of the crystal? I mean, if you are following the electron, then you have the crystal and the laboratory and everything coming towards you with the same speed as earlier the electron had relative to the laboratory. Which means that if you have some oscillation, then this should come from the crystal itself. How is this possible? I mean, atoms, well, if you go to the nucleus, it is heavy, so you will have very short wavelengths, which is couldn't give any pattern like that. If you look to the electrons, well, the electrons are moving around. They have whatever speed connected with energy levels, etc. They could not create any specific pattern in the same way. I mean, they have all different energies, etc. It's not possible. So then you say, well, maybe you have some reflection or resonance between the layers of the crystal. Okay, let's suppose that you can have this. In this case, it should be connected only with the distance between the layers. But if you look to the Bragg's formula of reflection, then you have also the incident angle of the electron beam, which means that you should have some variation depending on how you turn the crystal, which is not possible if you have some resonance between the layers, and it should be independent of the angle. So also this doesn't work. So you have here a situation where you could not have a reflection pattern as you see in this image. It's not possible. So what does it mean? It's only one possibility. I mean, the reference system of the laboratory works perfectly well, and the reference system of the electron doesn't work at all. Not only, but any system of reference other than the laboratory reference frame becomes out wrong. It doesn't give this pattern of reflection. So you have two choices, or everything is wrong. I mean, you have to, even based on an experiment, I mean, you must be completely wrong everything, or relativity theory is wrong. Since we have seen earlier that we have a serious problem already to explain the light speed and the extension of fields around charges, I suppose that the relativity theory must be wrong. So we save all the rest of physics, we just say special relativity is wrong in a certain sense. I mean, you have special relativity works very well in the laboratory, but if you move the reference frame to something else, then it doesn't work anymore. What does it mean? There is only one possible solution to this, and that is that the Earth is surrounded by some sort of medium which are following the Earth in its path through space, and which means, of course, that all material bodies have some sort of medium surrounding them, In the case of the Earth has a very big mass, so it's a very strong medium, which so the small objects on the surface of the Earth, their surrounding medium is completely neglectable compared with the Earth's medium. So you have what you in the old times you would call this frame dragging ether, which is more or less correct. I mean, more correct than Einstein in any case. But the problem with the ether theory was that you cannot do very much with the ether theory. I mean, you have no nice formulas that you can use to calculate things. And the relativity theory of Einstein, on the other side, had some mathematics, even if it was wrong. I mean, you could make some calculation using it, and you get some nice results. So this was chosen as correct, but in fact, ether theory was more correct than Einstein. So how come then that you have a lot of experiment in Earth on the Earth surface showing that relativity is correct? In fact, if you look to the laboratory experiment, you'll find that the local reference, which is the medium, is the same as the inertial reference frame of Einstein. So both of these theories should be coincide and be correct person on the surface of any big mass lump, let's say any planet, sun, or whatever, should give the same correct results. Okay, so now we have shown that there is a serious problem with the relativity, and now what is interesting for us is that the Earth must be surrounded with some sort of medium, which means that we have something surrounding all masses, in fact, and that the space is full with something, and so the relativity theory is in principle wrong, even if you can use some of its equation on the surface of the Earth. So in the following video, we will have a look into what is this medium surrounding the Earth or any particle or whatever, and we will try to understand how this can work. Okay, so you're welcome to the next video.